Okay. So, today's lecture will be on Kolmogorov 4/5 law. This law is in the real space. So far we focused on Fourier space description, but now we will go to real space description, and this was derived in 1941. Okay. Kolmogorov wrote 3 papers. The first 2 papers are related to what I will do today. In fact, this is the second paper, the dissipation. So, I gave you all the papers, so everybody has those 3 papers. This is the second paper where he derives what I am going to show today. Of course, those papers are very cryptic, he just writes one line, but to derive it, it takes quite a bit of effort, which I am going to do today. Okay. So, this is there in Kolmogorov's second paper, 1941. And it is in a Russian journal, but it has been translated in English. So, what does it mean? So, we have take 2 points in real space. Now, this is in real space. So, we are going to go to real space, which are separated by vector L. Okay. So, if I take a coordinate system, this is vector r and this is vector r plus L. So, difference between 2 points will be L. So, there will be velocity at these 2 points, v1 and v2. So, take the difference between the velocity at the 2 points with delta u, take the projection of delta u along L. So, that is what is meant by parallel. So, I take the projection. So, I take the projection like this and difference, perform average. Now, this average is supposed to be ensemble average, means I take many copies of turbulent flow started with similar initial condition, not same initial condition, similar initial condition, and then do this average over many copies. This is called ensemble average. So, if I do this average, then what I will get is minus 4 by 5 epsilon u, which is the dissipation rate, times the distance between the 2 points. This L is a distance scalar. Okay. Of course, this is under certain assumptions like viscosity going to 0 limit, steady state. So, I will put similar assumption which I did before, same assumption, but this is in real space. Okay. And this is connected with phi third, which is easy to see. How is it connected? So, one thing is there are some details. So, assuming that it is a fractal structure, or so cube order is L. So, what do you expect about delta u squared? Now, of course, it will be parallel only, no, but spectrum is connected with velocity difference between 2 points along all directions. So, what I think let's do that bit later. Okay. So, I think I do not want to get into. So, this connected with phi third, you can derive it. Okay. So, I will derive it maybe in the next class. Okay. So, this is easily derivable. So, my objective today is to derive this. Okay. Now, I will skip some of it, I will give those notes where all the details are there. So, this bit of tensor algebra, but I will give the main steps because the steps are quite involved. So, I can't do it on this computer. Okay. So, the steps are, first I have to define what is homogeneity and isotropy, isotropic tensor, second order, third order correlation function, third order structure function. So, these are all has to be done. Okay. Then this law comes, 4/5 law, and then I will compare with spectral theory, and I will describe about the higher order structure function, which is generalization of Kolmogorov structure function. Okay. So, let us start with what is homogeneity and isotropy. This is assumed by Kolmogorov in his paper. So, before going to isotropy and homogeneity, I have to talk about something about isotropic tensor, because we need this for the derivation. So, there in fact, so it is so there are 2 ways to look at it, but let me just give the simpler version. So, I think everybody has done electrodynamics in your undergrad classes. No? So, I am just going to invoke that algebra. So, I have some charge, charge, and I want to look for potential from this origin. So, I make it this thing. So, charge, they are not single charge I know the potential, it is 1 over r, but I have many charges, then I want to find the potential. So, if you recall V of r, so you expand for all charges. So, how does it go? First is sum of all the charges, which will be total charge, divided by r. 4 pi epsilon naught I am not writing in CGS. The second thing is, well, the total is q, but they may not be, it is not a point source. So, there is scatter. So, imagine that there are two charges which are, so one example, you know that there is a plus and minus separated by distance d, it is a dipole. So, dipole total charge will be 0, but it has a potential, no. So, how do you write that part? So, there is a dipole, electric dipole, so which is P. So, now I have to construct a scalar given P. So, P is a vector. So, how do I construct a scalar? So, now they have another vector called r vector. Okay. I dot this with r, divide by some function of r. Now, we know that it goes as r squared, right, 1 over r squared. So, there is one r dimension is already there. So, there will be r cube, apart from prefactors of coefficient like 2, 3 and so on. So, this is how we construct for dipole. Now, third is, I may have plus minus, but net dipole I want to make it 0. So, there is a minus here and plus here. Now, my net dipole is 0, but still it has a electric field and potential. So, this is a quadrupole. So, how do I make the quadrupole? So, it is a higher order term. Now, that comes as q r I r j. So, r is a vector which is component. So, r I r j. So, this is q. Now, q I j. Now, how do we construct q I j? Q is a second rank tensor. It has two indices. So, because it is not a vector anymore, like P is a vector, no, dipole moment is a vector, but it is not a vector, it is bigger object, because P is 0 for this. So, q I j is written as following. So, there are, so we have basically for each charge there is a vector. So, he calls, like if you look at Griffith's book di, each charge is separated from the origin by distance di, di vector. From the di vector I construct the following tensor. Okay. Now, I am not going to worry about the coefficients, that you have to do more work, but it will be a. So, there is a vector d, this is vector d here, no. So, I am going to let's focus on d alpha. I do not want to say alpha is that label of the charge particle, alpha equal to first charge, second charge, third charge. So, d alpha I, d alpha j, this is second rank, no, it requires I j contraction plus b delta I j. So, Kronecker delta function is when I equal to j it is 1, otherwise it is 0. Okay. Now, for convenience this is also derived by d alpha squared. So, this one and this one have the same dimension, right, because it is dimensionless, d by d by d squared, and this is also dimensionless, and a and b are some function of, it is a number, it is a scalar quantity. So, this is second rank tensor. Now, this for single charge, but you can do for more charges by summing up. Now, you see that A, B will be computed in books by like Griffiths, but this is second rank tensor, this is of this form. Apart from the numbers, which is I think 2 by 3 minus 1 by 3 or something like that, apart from the numbers, this is the form. this has to come from mathematics. Okay. This also will work for magnetic vector, magnetic potential. I mean, any of this, I need this is to be scalar, and scalar will be expanded like that. This is, I mean, pure tensor algebra. Now, why is it called isotropic? Look, now this is a tricky part. Any vector, let us say constant vector A, under rotation satisfies certain property. Now, this you might have done, right? You have done this. What is the definition of a vector? So, in mathematics, vector is not called with objects having length, has a magnitude and direction. That is not a proper definition. So, what is proper definition of vector? So, what is it? It transforms exactly like a position vector R. So, if I rotate my coordinate system to like this, my A component of A vector will not be same as Ax Ay, it will become Ax prime Ay prime, but that will transform exactly like x comma y, because position vector also will change. Instead of x y, now it has become x prime y prime like this. Okay. Anyway, this I will not get into it. Okay. I mean, this is a big derivation. So, this is how you define vector. Tensors are also defined just like that. Second rank, third rank, this is a definition. But what is isotropic? Isotropic is that if I rotate my, so for charge particle, point charge particle, my vector field E vector at different positions are different, right? It changes direction. So, if I take same R, it changes direction E, but its magnitude remains same, and also its direction is radially outward. So, it is like isotropic, though it is not exactly same because the vector has changed. Here the definition of vector, A vector, any vector under transformation will transform in particular way. So, isotropic tensors have even more stronger constraints, that these objects should have certain properties. Okay. Now, for isotropic vector E, now I am going to, so this is one way to look at it. Okay. This is one part of it. So, the source I would like you to see, if you are interested, is Bachelor's book on homogeneous and isotropic turbulence. Homogeneous isotropic turbulence. Okay. Now, so isotropic vector is easy, isotropic scalar is easy to visualize. Isotropic scalar is, if I go around, I should get the same value if I am distance r away from the source. So, isotropic potential is 1 by r, is a isotropic scalar. Is that clear? Isotropic scalar. Scalar is, by the way, temperature is a scalar field, because when I rotate my coordinate system, I get the same value at that position, but temperature need not be constant or radially symmetric. That is the additional constraint. From the center of the source, if my temperature is same at all points away from, at all points on a sphere of radius r, that is the additional constraint on the scalar. Is that clear? And that temperature field, which is only function of r, is isotropic. For a point source, that will be the, well, under condition, it is possible that it may develop, the temperature may spread, but it will spread symmetrically if it is point source in the center. Now, we can also think of isotropic vector. So, electric field, if I have many charges, electric field is will have different in different directions, right, but this is still a vector. But isotropic vector is, if I go from one position to other position in the sphere, my magnitude remains same, but it is pointing outward. Okay. So, that will be isotropic vector, and that will be r vector multiplied by ar, right. This is the form. There is one more form which I will not discuss. It could be like tangential, and we can construct it, but this is what you should think of today, or ar ri. So, this isotropic vector isotropic scalar. What about isotropic tensor, second rank? Can you make a guess? Now, this is not easy to visualize. The vectors and scalars are easy to visualize, but second rank is not so easy to visualize. Okay. So, I can use this idea. So, construct a second rank tensor which is isotropic, only function of distance r. So, that will be T I j is A of r, r I r j by r squared, let us keep that, plus B of r delta I j. So, this is a isotropic second rank tensor motivated by this discussion on potential. Okay. So, this I can't visualize actually, second rank tensor, I mean it has two component and rather two indices, not two component, it has 9 component in 3D. Okay. Is that clear? So, I am going to use this result, I need this, that is why I am giving you this background. Okay. So, everybody is happy with it. So, more discussion on Bachelor, because we will not finish otherwise. Now, homogeneous isotropy of turbulence. So, this is from a simulation on a periodic box which we did in our lab. So, this is vorticity squared. This scalar quantity is magnitude at different positions are shown. Now, we can see that like it is not coming from a point source sitting in the middle. This is homogeneous in the sense though no position is preferred. So, homogeneity means population is equally distributed on this planet. It is not, but that is why it is not homogeneous. If something is some position cannot be identified, the unique position, then is homogeneous. Okay, the universe is supposed to be homogeneous. Okay, there is no heaven or something like that, it is invisible universe. So, this is homogeneous in the sense there is no position which is unique position in this space. What about isotropy? If I rotate this box, then I get very similar structure. So, that is a isotropy. So, we have homogeneous, which is the properties are independent of x. Of position. I will be more specific in the next slide. Isotropic is independent of rotation. And we also need something called stationary. That means it is independent of time. So, if I look at it now or later, it is looking approximately same. But this is a dynamic system. So, you will not get exactly same phenomena or same distribution, it will change, but it will be randomly changed in this position. Okay. So, independent of time. So, homogeneity means independent of space and stationary means independent of time. But of course, visually is one thing, but now we want to quantify it, and quantification is done by correlation tensor, velocity correlation, second order correlation. Okay. So, this is where we are. Now, we are making good progress, but if you are not getting my point, please stop. Okay. Is that clear to everyone? Isotropy, homogeneity.
Is there an example?
Yeah. So, for example, potential of a charge particle, point charge is isotropic, but not homogeneous, right? Because we can, let us go back. So, we have point source. So, go to any direction, you will get the same potential, but potential here and potential here are different. It goes as 1 over r. So, this is isotropic, but not homogeneous. Okay, and there is situation where it is homogeneous, but not isotropic. it could be like constant field is homogeneous along that direction, but it is not isotropic because when I rotate I will not get it. Okay.
Channel flow is what that is anisotropic and inhomogeneous. Both.
It's so along the direction of flow, it is homogeneous along that direction. So this homogeneous I said about every direction, but you can say, let us say homogeneity along x. What does it mean? If I travel along x, I get the same field. So if I whatever get here is same as here. Okay, so that is homogeneity along x, but it is not homogeneity along y because there is parabolic profile, so things change along y. But we will assume that we are homogeneous isotropic, and which for turbulence, and which is quite a good approximation away from the walls without external field like gravity or magnetic field. If you do not have those fields, then you shake it up in a periodic box, it is homogeneous and isotropic. Okay. So now we are going to look at second order correlation functions. So I am going to focus on 2 points here, r and r plus l. So these are our notation. So r is a vector, r plus is a vector. The difference between 2 points is also a vector l. Now I measure velocity at these two positions, u of r and u r plus l. Now of course both are vectors, so we can have correlation which is product, but it is not really because it is a vector, so you can't have just multiply, right. So multiply x component with x component, x with y component, x with z component, and so on. So the shorthand notation is ui uj, I takes value 1 2 3, j takes value 1 2 3, but you see this is the first position x, so I will call this is r and this r plus l. Of course in general it will depend this correlation function, let us assume same time, I am assuming right now same time. So it will depend on x, y and t, right, these are the arguments. So this is the general property of the tensor. Now I am doing average, okay, the velocity field fluctuates, so I want to average it out, so that is only function of x, y, t, is not property of the sample, right. I mean, so we wait for some time, average, then you find it's function of x, y, t. Now I am not doing temporal average, and that is why the t is kept here, is called ensemble average. If I average in the same box, then t will go away. So it's a we will take many copies, and at a given time we average. Is that clear to everyone? No, not clear. So I start with initial conditions, system 1, system 2, system 3, system 4, system 5, change the initial conditions, okay, but total energy is the same, random start. So this will give you some ux in ui, this will give you ux ui at a given time. So all of them will give you velocity field. Now take velocity field at ux and ur plus l of each box at given time, then average, okay. So this is at a given time, but from different systems, and this is called ensemble. Ensemble means many systems. Is that okay? Now if it is homogeneous, then what do you think? So what will it depend on? It can't depend on x and y together, on both x and y. It will depend on the difference between the two. If this position were shifted by, let us say I take it here, but I translate them, just translate. So translation is not changing the direction. I have these 2 points, I just translate it in any direction, but do not change the orientation, okay. So it will depend only on the difference between the two. So this becomes, for homogeneous, this is Cij, it does not depend on x and y separately, it depends only on vector L, so it would depend on Lx, Ly, Lz. So this is homogeneous. So first put homogeneity, now then you put isotropy on top of it. I want homogeneous and isotropic both. So what do I do? So it says that not only this L, but this L, by keeping the distance equal, if I rotate it. So this point is fixed, but my second point is rotated here, I should get same correlation. Of course, this is a tensor, so my components will change, but I should get, well, I mean I am going to show you now that it should be only function of L. It cannot depend on direction. I will be more specific in the next slide after this. So, magnitude of L, and if it is stationary, then T also will disappear. It is only function of L. Cij and L is magnitude of vector L. Yes.
If it is stationary, then we don't have to do ensemble average, right? We can take different
Yes.
times.
Stationary, then you can take at different times of the same system, and that is what we typically do in simulations. We assume time average as equal to ensemble average. Okay. So, this is what is assumed by Kolmogorov. Okay. So, I am putting the same picture again, and this is same, but now I put vector L here, and isotropic means it becomes small l. Now, isotropy, remember I said it is isotropic. So, my second rank tensor has this, is independent of direction of L. So, if I rotate it, I get the same thing. So, that means n, what is vector n? Vector n is unit vector L by L. This is my definition. So, shorthand, I do not want to write L, Li, Lj, I write Ni, Nj. So, this is what I motivated, no. So, isotropic tensor. So, since it does not depend on well, basically if I rotate, I get my system should be the same. Okay. So, that means it is Ni, Nj and delta Ij. For vector is easy to see, it should be just Li, because it depends only on L vector, but second rank tensor will be Li, Lj. This is coming from Li, Lj plus delta Ij. Okay. So, this is my motivation. I said isotropic, since Cij is isotropic, it is not the same number for all Ij, that will be scalar, but since it is a tensor, it has to be of this form, and this is only function of L, C1 and C2 only function of magnitude L. If I know the magnitude, I know this. Now, I will make it more specific. So, this is the form, and now you can see the beauty of this expression. So, we will go to the next slide. Okay, I have one more point. Since U is incompressible, so if I take the derivative of this with related to, well, I can take with related to L vector L vector Li, Lj, sorry, Lj. So, it will act on this one, it will not act on this, right, and since I am doing over Lj, summing over j, it should get 0, yes or no. So, this implies this equal to Ui U, I am going to call it prime, because this R plus L. So, this is a notation going to come very soon. So, R plus L will denote by prime, instead of writing R plus L, we write prime. Now, derivative with related to Lj same as with related to R plus L j is the second variable which I am taking derivative. So, del j prime. So, Ui is a constant for it. So, it basically acts on this del j, and this is 0. Okay. So, incompressibility on the velocity, one of the velocity, if I take the derivative divergence, I should get 0. So, I am taking divergence on this if I do derivative with L. Now, finally, by the way, the point is, when I do the ensemble average, R disappears, R does not appear here. So, it is only function of L. So, I have to take the derivative with related to L, R is not there anymore. So, that is why this is, when I say this, I means del Lj, Cij L, this is 0, is that okay, and I need this condition. This is helpful, I am going to only state the results what we derive from it, but we use this for our algebra. Okay. Now, I made this picture smaller. So, this is my same equation C1L, C2L, Nij. Now, I choose my coordinate system like this. So, my n vector of course is along L, right, n is vector L by L. So, this small picture, everybody see that? Is it too tiny or visible? So, this vector L and n vector will be unit vector along that, fine. Now, choose my coordinate system. This is x axis x1, this is a y axis x2, and third one is towards me above the page x1, x2, x3 is a 3 component. I choose local coordinate system with x1, x2, x3, x1 is along n. Is that clear? Yes.
The Cij is a function of bold-faced L. That means it's no longer isotropic, right? Because it's still a function of the vector L.
Okay, so you are right. So I can make it L, small L. Okay. But by the way, here these are function of L actually. So strictly speaking, I should keep L. No, I should keep L actually. So the L is coming here. So it will become clear in a minute. Okay, so I am take the component and see what happens. So x1, x2, x3. Now I am going to substitute that particular component. So if I look for correlation C11, actually let's do the algebra before I put my results. C11 of vector L, what is it? So C11 is along x direction or along x1 direction. So it will be C1 L. And what about N1? N1, N1. What is N1, N1? What is N1? 1. N2 is 0 and N3 is 0. There is no N is along vector x component. It has no y component, z component, right? My n is along this direction. So this becomes, both of them becomes 1. What about this one? Delta 11 is 1. Okay. So C11 is C1 plus C2. What about C22? C22 of L. So C22, what is this guy? N1, N2, N2? N2, N2, 0, N2 is 0. So this part is 0. What about this one? This is 1. So C2 will give you only C2 of L. C3? C3 is again, so C3 is coming towards you, it is just this again 0 and C2 of L. Because of isotropy, the correlation, so if there is a vector L, isotropy means in the perpendicular plane it should be same. So along x2 and along x3 my correlations are the same. So the two vectors, there is a vector here, velocity vector and velocity vector here. So I am taking the component correlation, my velocity like this, that is C11, my velocity like this, it is C22, velocity like this is C33. Is that clear? And C22 and C33 must be equal. What about C13 or C12? What is this? Why is it 0? Okay, from the formula it is 0, but can you argue why it is 0? It should be 0 for isotropic tensors, isotropic velocities. So look, this is my velocity along this direction u1, velocity along this direction I want u2. Okay, this is a correlation of C12 means u1 u2 prime. Now prime I already introduced the notation. Prime means r plus l, shorthand, otherwise it is just too much to write. So now if u1 is fixed, well, at a given time, what is the probability of finding u2 upward and u2 downward? Half. If so, it is random. So sometimes u2 will be like this, sometimes u2 will be like this. That is why this u1 u2 prime is 0. Okay. So in fact, any of these things, if we have velocity like this, either a scalar or a vector in the perpendicular direction. Scalar multiply, because that can take both positive and negative value, you will get 0, or a vector component in the perpendicular direction, that can take this and is 0. So, all the cross terms are 0, is that okay? So, this is a property of, I mean these all captured in my formula here, this formula, whether this is true for not only this choice of coordinate system, but true for any coordinate system I choose. I have to just transform by rotation. I could have chosen my x coordinate system to be like this, like that, and fine, just to do the transformation. So, this n2 need not be 0, if I do like this, n2 will not be 0, right. Okay, so this is what I have in my stuff. So, this C1 plus C2, so I should, so this C2. Now, we write like this U squared FL and U squared GL. So, U squared is the U1 multiplication at the same position, okay. This is just U1. So, U1 squared, it is U bar squared. Should it be same as U2 squared? Yes or no? Why can't I say that? It is isotropic. So, U1 square must be same as U2 squared. So, it is isotropic. So, velocity magnitude in that direction take component, or y direction or z direction should be same. So, that is why I have the same thing sitting here and sitting there, fine. Now, so this one, if I remove this magnitude U squared, then this function will be dimensionless, and for L equal to 0 it becomes 1, right, because U1 equal to U1 prime. So, FL is 1 for L equal to 0, and it decreases. In fact, correlation will decrease when you increase L, right, you go away from the same point, correlation is expected to decrease, is highest correlation. So, it is maxima at L equal to 0. Okay. So, this part I am skipping, this derivation I am skipping, this one function you can expand it, it is 1 minus L square by lambda square, it goes in this form, and G also goes with this form. Now, R, F and G are they related to each other? Now, they are related because there is a constraint that Cij del j prime is 0. If I take the derivative of this with respect to L, I should get incompressible condition kick in, and I get the relation, which is there in the notes, I will skip, it is quite a bit of algebra, and this gives the relation G and L F are related like this. So, I take the L derivative, so this is the derivative of L, okay, and we can plot both F and G, but I plot it together. So, CII is a contracted, which will be, so this becomes 3, right, NINJ, no sorry, NINI is what, 1, NINI is 1, and this gives you 3, delta 1 1, delta 2 2, delta 3 3, okay. So, this part I will skip, please look at the notes and do it. So, this is CII by U squared, and it has, this part is parabolic, 1 minus phi L square by 2 lambda square, it comes phi algebra, okay. Now, this part goes as L to the 2/3, is from Kolmogorov theory, okay, because is 5/3 will, if you do the Fourier transform, we get 2/3. This I will do in the next class, and it vanishes finally for very large L. So, there are two important things, is parabolic and this is the power law. This from Kolmogorov minus 5/3, K minus 5/3, and this is by maxima at L equal to 0. Now, this lambda is very specific, it has a specific name, it is called Taylor microscale, okay. Now, this coming from this definition. So, lambda is called Taylor microscale, and that is connected with the dissipation rate. Now, this is also quite a bit of algebra. So, I am connecting epsilon u by vorticity, given correlation function I can compute vorticity correlations, and that gives you this. Is doable, but you have to just dig in and you have to do the algebra, okay. And once I know lambda from dissipation rate and viscosity and u, I can compute Reynolds number, fine, and Reynolds number that is called, so this is lambda is called Taylor microscale. And this is called Reynolds number based on Taylor microscale. So, this is multiplied by lambda, u bar lambda by nu. So, instead of system size, which is for Reynolds number, so RE, remember what is RE? RE is URMS L by nu, that is definition of RE, yes or no? But RE based on Taylor microscale is u bar, which is not URMS, u bar and this u bar and URMS are different. Okay. Now, this I will again ask you to look at the notes. So, u bar is just a factor, prefactor, lambda by nu, and that is connected with RE by this square root of RE and factor 20 by 3 square root. Okay. This can be shown, this is there in my notes. Now, this is about second order correlation function. Now, we have a long way to go. I mean, we just have to. Is that any question on second order correlation function? So, we have f and g, C11, C22, and so they are second order correlations we can compute given velocity field. It is isotropic, so it depends only on L. But remember, it is not a number, it is a tensor. So, we have C11 and C22, they are different, right? They are different here, f and g are different functions. So, it is not a single number, but this is the beauty of this tensor which captures all of it in one formula, okay, respecting isotropy. So, it tells you the C1, C2, C1 comma 1 2, C12 is 0, C11 is number, C22 is same as C33, all that follows from it.
So this correlation is always 0 or only it is applicable in homogeneous isotropic?
Homogeneous isotropic. Homogeneous isotropic. Anisotropy, not all, some of it will go through, but not all. Okay. So, with magnetic field this will not work. Okay. So, thank you.